Hey friends, welcome. Today we will be discussing Debye Huckel theory. This theory it is also known as Debye Huckel theory for strong electrolytes. It is also known as Debye Huckel theory for the ionic solids. So basically, this theory was given to explain the behavior of strong electrolytes in dilute solutions. Now we have studied several theories which explains the behavior of weak electrolytes like acetic acid, and we have studied Oswald dilution law, and there are several other theories also. So this Oswald dilution law, it holds true for dilute solutions of weak electrolytes, but this Oswald dilution law it cannot be applied to the dilute solutions of strong electrolytes. So there was a need to obtain a theory which could satisfactorily explain the behavior of the strong electrolytes. So Debye and Huckel, basically in say 1923, they developed this theory, and this theory was known to be Debye Huckel theory of strong electrolytes, and this theory could explain satisfactorily the behavior of dilute solutions of weak electrolytes up to say 0.005 molar or below this dilution also. This theory is based on several postulates, so we will be discussing those postulates one by one, and then we will be moving on to the mathematical derivation. And basically in this video we will be obtaining the value of psi, which is the electrical potential over here. So first postulate, it states that every strong electrolyte is completely ionized at all dilution. So the first postulate, it says that each strong electrolyte is ionized completely, or there is 100% ionization of the strong electrolyte in all dilutions. In all dilutions that means whether I prepare say a solution of say 1 molar solution, or I prepare say very dilute solution of any strong electrolyte. Say suppose I am taking NaCl, which is strong electrolyte. So whether I am preparing 1 molar solution or 0.001 molar solution or say 5 molar solution, so in any particular solution the sodium chloride will be ionized in Na plus, or it will be present in the form of Na plus and Cl minus ion. So this is our first postulate. The second postulate is, it says that there are two types of forces that are acting on mobile ions. In solutions we all know that the ions are in continuous mobility. Ions are not stationary at one place, but they are continuously moving. So when ions they are moving in the solution, basically they will be influenced by two types of forces. The first forces that the ion will experience is the electrical forces. So these electrical forces are due to the electrical forces, or it could also be referred as electrostatic forces between the oppositely charged ions as well as the like charged ions. And the second type of force that the ions may experience are the resistance due to the viscosity of the medium. So resistance due to the viscosity of the medium, and this is known as viscous drag. So this viscous drag basically will reduce the velocity of the ions, and this electrical forces will increase the velocity of ions, because viscosity, more the viscosity, lesser will be the speed of the ions, and the higher amount of electrical forces will increase the velocity or the mobility of the ions, and hence resultant force could be written as the difference between the electrical force and the viscous drag. So resultant force which are acting on our ion will be the difference of the electrical forces and the viscous drag. The third postulate, it states that the forces that are acting on the ions and that are governed, that are basically electrostatic forces, and they are governed by Coulomb's law, and Coulomb's law we know it is given by F is proportional to Q1 Q2 upon R square, where Q1 and Q2 are the charges on the ions and R square is the distance between the two ions. And the fourth postulate, it states that every ion is surrounded by the number of oppositely charged ions, and such an atmosphere formed, it is referred as the ionic atmosphere. So over here, suppose if we say that we have a positive ion, then this positive ion will be surrounded by several negative ions, and similarly if we have say any negative ion, this negative ion will be surrounded by several positive ions, and this this sphere that is formed of negative ion around the positive ion is known as the ionic atmosphere. And this formation of ionic atmosphere makes the strong electrolyte different from the weak electrolyte. The deviations that we are seeing in the solutions of strong electrolyte is basically because of the formation of ionic atmosphere. In weak electrolytes, ionic atmosphere basically it is not formed, and in strong electrolytes there will be a formation of ionic atmosphere, and hence the deviation, or hence we could say that strong electrolytes, they are not following the laws which were given for the weak electrolytes. So these are the four postulates on which the Debye Huckel theory is based. Now we will be moving to the mathematical derivation. So as I have told, we will be obtaining the value of the electrical potential psi over here. So first we will be defining the value, or we will be first defining the electrical potential. So electrical potential at any particular point, it is defined as it is the amount of work done in bringing a unit charge which is present at the infinity to a particular point. Say suppose if we are considering that we are having, or there is a unit charge that is which is lying at an infinite point, then from that infinite point, if we are bringing that unit charge from infinite point to a given point in the solution, then the amount of work done is represented as electrical potential, and it is represented by psi. Okay, now suppose if we say that psi is the potential which is present at any particular point which is in the vicinity of this positive ion. So psi is our electrical potential which is in the vicinity of this particular positive ion, and then we are bringing any particular positive charge from infinity to this positive ion, then the amount of work done for bringing this positive charge to nearer to this positive charge will be given as amount of work done. It will be given as, we know that any work done will be amount of physical work done will be given as force into displacement. Now suppose if we are considering that Z plus is the valency of this positive charge and epsilon is the electrical charge, then Z plus epsilon will be the amount, or will be the weight of this positive ion, and we are bringing this positive ion nearer to this particular point, and that is the amount of displacement, and that displacement is equal to the electrical potential psi. So the total amount of work done when we are moving the positive charge, it will be given by Z plus epsilon psi. Similarly, if we are bringing say any negative charge from infinity to again this particular point, then the amount of work done for the negative ion, and this is for positive ion, so amount of work done when we are bringing negative ion will be given by minus Z minus epsilon psi. Okay, over here Z plus and Z minus are the valencies, and they are numerical values only. Okay, so this was the first thing. Second, now suppose if we are considering we are having a dilute solution, so we are considering that n plus 0 and n minus 0 are the concentrations of the positive ion and negative ion per unit volume in a given dilute solution per unit volume in given dilute solution, then according to Maxwell-Boltzmann distribution, the distribution of the particles in any given dilution, or the distribution according to the Maxwell-Boltzmann distribution law, according to the Maxwell-Boltzmann distribution law, the distribution of the ions in the solution, it will be given by, we know the Maxwell-Boltzmann distribution law. Maxwell-Boltzmann distribution law, it is given as Ni is equal to Gi e raised to minus Ei by Kt. Okay, so over here Ni are the total, Ni are the number of particles, Gi is the statistical weight factor, Ei is the energy, K is the Boltzmann constant, and T is the temperature of the system. So same thing we could apply to obtain the distribution of the particles in the solution. And suppose if we say that we want to obtain the distribution of particle n0 which is present in a given dilution, n plus and n minus are the concentrations of the positive and negative ions which are present in our solution which is under consideration, then n plus will be given as n plus 0 e raised to, now Ei is the amount of energy, and this amount of energy is nothing but it is equal to the amount of the electrical work when we are talking about any system which is performing electrical work. So over here in place of Ei we will be substituting Z plus epsilon psi minus upon Kt, and similarly n minus will be given by n minus 0 e raised to minus Z minus epsilon psi by Kt. Okay, so both these expressions will give us the distribution of particles in a considerable solution for n plus and n minus. Okay, and over here when we observe both these equations, then we will find that this will become minus minus plus, and hence we will have n minus will be greater than n plus. Okay, so that means that surrounding any positive ion there will be larger amount of negative ions, and surrounding any negative ion there will be larger amount of positive ions, and surrounding every positive ion there will be larger amount of negative ions, and this represents the formation of the ionic atmosphere. Okay, this represents the formation of ionic atmosphere. Now again we will define one more term, that is total charge density. We will be defining one more term, and that is total charge density. And total charge density, it is represented by rho e, and this total charge density at any particular point it is given as it is the excess of either say positive or negative electricity per unit volume at a given point. Okay, so over here this total charge density is either say positive or negative electricity per unit volume. We all know that the solutions or the electrolytic solution is always electrically neutral. Now what does this total charge density? It means that if we are dividing our solution into say small segments of 1 ml by 1 ml each, then at any particular ml what will be the excess amount of charge? Say either there may be, because we all know that the ions are migrating, and when the ions are migrating, then per unit volume there may be extra positive ions, or per unit volume there may be extra negative ions. So per unit volume at any particular point, as a whole our solution is electrically neutral, but at any particular point there may be excess positive ions or there may be excess negative ions. So over here the total charge density, it gives us the value of the charges which are present at a particular point of unit volume. Okay, and this is the excess amount of either positive ions or excess amount of negative ions, and hence the total charge density rho e will be given as excess amount of positive ions, or the total number of positive ions will be given as n plus Z plus epsilon. So this will give us the total amount of positive ions minus n minus Z minus epsilon. This will give us the total amount of negative ions. And say suppose if positive ions are greater, then the value of total charge density will be positive, so that shows the excess amount of positive ions. And if negative ions are greater, then the value of the total charge density will be negative, and this represents the excess of negative charges are present in the solution. Now we have the value of n plus and n minus over here. So this values of n plus and n minus, that is this values of n plus and n minus, we will be substituting in the value of total charge density, and hence our expression will become, we will have n plus 0 e raised to minus z plus epsilon psi by kt, and then we will have z plus epsilon minus n minus 0 e raised to, what I will do is, over here we have minus and this minus, so this will be plus. Okay, so we will have e raised to z minus epsilon psi by kt z minus epsilon. Okay, so this is the values. Now we want the value of the total charge density. So over here we will be considering two cases. The first case will be the simpler case, wherein we are considering a uni-univalent electrolyte. So uni-univalent electrolyte, that means the cations and anions are one, like we have NaCl, KCl and several other ions. So wherein we will have the values of z plus is equal to z minus, and that is equal to 1. And similarly we know that in any particular univalent electrolyte, the number of cations are equal to the number of anions. So I could write n plus 0 is equal to n minus 0, and that is equal to, suppose we say, n. So over here we will be substituting these values in this equation, and hence we will have rho e is equal to, this will be n e raised to, this will be 1, we will have epsilon psi by kt, and this will be 1 and this will be epsilon minus n e raised to, this will be minus. Okay, so we will have plus epsilon psi by kt, and then we will have epsilon. So from both these terms we could take n epsilon common out, and we will have e raised to minus epsilon psi by kt minus e raised to plus epsilon psi by kt. Okay, now this particular term, it is similar to the power series, that is, suppose if we have e raised to x, then it will be 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, and so on. Okay, so this is similar to the power series. And over here suppose we are considering that we have x is equal to epsilon psi by kt. Okay, so over here when we solve, or when we substitute the values of epsilon psi kt, then the value of this x is very less than 1. Okay, it is less than 1. It may be of the order of 10 raised to minus 10, 10 raised to minus 20, and so on. So the value of x is very less, and if we are taking very smaller value, and if we are squaring and cubing it, then it will be very small value. So what we could do is, we could neglect all the square, cube and higher terms, as these values will be very less as compared to 1, and it won't have any influence on 1. Okay, so similarly if we have e raised to x, we will be using this solution, and if we have e raised to minus x, then there will be minus sign over here. So hence the value of our charge density rho e, it will be n epsilon into 1 minus, as this minus, we will have epsilon psi kt minus 1, and this will become again minus because this will be plus, and minus epsilon psi kt. So this one will be cancelled out, and we are left with this will become -2. So we'll have -2, and this epsilon will give us epsilon square psi by kt. So this is the value of the total charge density when we are having a univalent electrolyte. Similarly, if we are looking at a general case, so for general case, suppose over here we will say that the valencies will be same, but it will not be equal to 1. Okay, then in such case what will happen is that the expression, that is this particular expression, it could be generalized to rho e is equal to epsilon, then summation. Okay, over here epsilon is not variable, so epsilon, and in place of the variables, that is n plus, we could substitute ni, z plus we will substitute zi, and similarly this z plus also will be substituted by zi. So we will have summation ni zi e raised to minus zi epsilon psi by kt. So this will be the general expression for the total charge density rho e. Now again we will expand this particular term, or this we will be solving it using the power series. So the value of the total charge density rho e will become, and again the higher terms will be neglected, summation ni zi, and we will have 1 minus zi epsilon psi by kt, and this will be multiplied, so we will have epsilon. First term will be summation ni zi minus all the constant terms I will be taking out, that is epsilon psi kt, and this epsilon will be epsilon square. So we will have epsilon square psi by kt summation ni zi square. Okay, so this will be our expression. Now further over here we all know that the solution that we are using, or the solutions of the strong electrolytes or any particular electrolytic solution, are always electrically neutral. So over here when we examine both these relationships, then over here we have the value of zi, and over here we have the value of zi square. So by the virtue of the overall requirement of the electrical neutrality, the first term will be neglected, because this is not maintaining the electrical neutrality. Over here zi, so I could substitute either z plus or z minus, while I have zi square over here, so this I could write it as z plus into z minus. So over here the electrical neutrality is being maintained in this particular expression, that is the second expression, while the first expression is not maintaining the electrical neutrality, and hence we will be neglecting this equation. So our final expression will become epsilon square psi by kt summation ni zi square. So this is the generalized expression for our total charge density. Okay, and this we could check for the univalent electrolyte also. So for univalent electrolyte we have ni, we will have ni will be equal to n, and we will have z plus will be equal to z minus, and that will be equal to 1. That is, I can write n plus is equal to n minus, and that is equal to n. So when we substitute over here, we will have for univalent electrolyte we will have minus epsilon square psi by kt, and then we will have n plus n, and that is 2n minus 2n epsilon square psi by kt. Okay, so this expression and this expression both are same, so hence this is our generalized expression, and that could be applicable, or that is applicable for univalent electrolyte as well as any particular electrolyte that we are taking. Okay, now the next step in this derivation is we will be relating variation in the electrical potential with the total charge density that we have obtained, and to do that we will be using Poisson's equation. So Poisson's equation, basically it is based on Coulomb's law, and this Poisson's equation, it relates the variation of the electrical potential with the total charge density, and Poisson's equation is given by del square psi by del x square plus del square psi by del y square plus del square psi by del z square, and that is equal to minus 4 pi rho e by d. Okay, so over here this is the Poisson's equation, and over x, y, z they are the rectangular coordinates, and d over here is the dielectric constant. Now this dielectric constant is, or the value of dielectric constant is constant for the solvents that we are using, and similarly this dielectric constant is the ratio of the permeability of the electrons in the medium to the permeability of the electrons in the air, gives us the value of dielectric constant. And we have also seen that, or we have also discussed earlier, that there is a formation of ionic atmosphere, and we know that ionic atmosphere is spherically symmetrical. So over here this xyz, it represents the rectangular coordinate system, while the ionic atmosphere which is forming is spherically symmetrical. So we need to convert this rectangular coordinates into the polar coordinates, and also over here in polar coordinates the value of theta and phi will be constant, and hence the differential of theta and phi will be 0. So when we are converting this equation into the polar coordinates equation, the value of theta and phi will be 0, and hence we will be not looking at those values. We will be directly looking at the value of only r, which is the distance, and the conversion of this into spherically symmetrical will be into polar coordinates. It is given as 1 by r square ddr of r square d psi by dr, and that is equal to minus 4 pi rho e by d. So this is the expression which gives us the value, or which is a conversion of our rectangular coordinates to the polar coordinates, and theta and phi are constant, and hence the differential, that is will be 0, that is d psi by d theta, d psi by d theta as well as d psi by d phi will be 0. Okay, now over here we'll be substituting the value of rho e. So we will have minus 4 pi rho e is the value of total charge density. Rho e is minus it is minus epsilon square psi by kt summation ni zi square. We have minus over here, similarly we have minus over here, so that will be minus minus, it will become plus 4 pi 4 pi epsilon square upon, we will have dkt psi summation ni zi square. Okay, now over here all the values except psi, that is all these values except psi, I am taking it equal to kappa, which is a constant. Okay, so all the values except psi I will be equating it to kappa square. So I am taking kappa square is equal to 4 pi epsilon square summation ni zi square upon dkt. Okay, all the expressions, all the values except psi, I am taking it equal to psi, that is 4 pi epsilon square summation ni zi square upon dkt. So our expression will be converted into, we will have 1 upon r square d upon dr r square d psi by dr and that will be equal to kappa square psi. Okay, so this will be our equation, and now this is the differential equation of a second order, or this is a second order differential equation, and this second order differential equation has several solutions. Out of that, one of the acceptable solutions we will be using, and that solution is given as psi is equal to a e raised to minus kappa r by r plus b e raised to kappa r by r. So we will be using this particular solution of this differential equation. This equation, it is been found that the value of the constant uh, over here a and b are the constants, and it is found that the value of b is 0. Okay, so value of b is 0. So when the value of b is 0, automatically this term, that is second term, will be removed, or second term will be removed from this equation, and hence we are left with only this equation, that is psi is equal to a e raised to minus kappa r by r. Okay, so this is what we are left with. Now in this particular equation we have constant a, and we have to find the value of value of this constant. Okay, so over here I have told earlier that the systems that we are considering over here is a dilute solution. Okay, or we are considering very dilute solution, and in dilute solutions we all know that the number of ions per unit volume will be very less, or we could take summation ni zi square almost equivalent to 0, and when this is almost equivalent to 0, kappa will be almost equivalent to 0, and when kappa is almost equivalent to 0, we know that e raised to minus 0 will be 1, and hence the value of psi will be a by r. Okay, a by r. Similarly, so this is the value of psi when we are considering very dilute solution. Similarly, in a very dilute solution, or in such a dilute solution, we all know that the distance between the ions are very large. Okay, that is, the distance between say two oppositely charged ions or two similar charged ions is very large, because the solution is very dilute, and hence the distance is very large, and hence the ions will not have much influence, or the two ions will not influence each other. So the potential which is present at that particular point, or the potential which is present near to this particular ion, will be the self potential of this ion, and the self potential of any particular ion, it is given by zi epsilon by d r. Again, zi epsilon is the charge, d is the dielectric constant, and r is the distance. Okay, so this is the value of the self potential at any particular point in very dilute solution. So this is the value of self potential, and again this is the value of potential in very dilute solution. So both these values are same, and hence we could equate both this equation, and hence we will have a by r is equal to zi epsilon by dr. Okay, so ye r will be cancelled out, and hence we will have a is equal to zi epsilon by d. So we have the value of constant a. So our expression will be converted into psi is equal to, we will have zi epsilon by dr e raised to minus kappa r. Okay, now further again we could expand this particular term, and again the higher terms will be neglected, so the result, also the expression, will become zi epsilon by dr into 1 minus, we will have kappa r, and when we multiply it, we will have zi epsilon by dr minus zi epsilon kappa by d. So this is the final expression which gives us the value of electrical potential at any particular point in the dilute solution of strong electrolytes. Now as you can see that this expression is made up of two terms. Now over here, this the first term, it represents the potential, or it represents the self potential of the ion, and the second term, it represents the potential due to the ionic atmosphere which is formed. Okay, so this is the self potential of the ion, and this is the potential which is potential due to the ionic atmosphere. Okay, and over here we all know that the magnitude of the ionic atmosphere will be equal and opposite to the magnitude of the positive charge. And similarly, when the ionic atmosphere is formed, then when the distance between the oppositely charged ion will be equal to 1 upon kappa, at that time this much amount, that is minus Zi epsilon kappa by d, this much amount of the potential will be generated, and hence this distance 1 upon kappa, the distance 1 upon kappa is regarded as Debye length. This 1 upon kappa is regarded as the Debye length, and this Debye length is nothing but it is the ionic radius, or the radius of the ionic atmosphere. Okay, it could also be considered as the radius of the ionic atmosphere, and generally the Debye length is of the magnitude of 10 raised to minus 8 centimeter, and the value of kappa, it depends on the concentration as well as the valency. That is, the value of kappa, it depends on the concentration of solution as well as the valency of the ions that are under consideration. And one example, that is, if we are taking, say, any univalent electrolyte, then for 1 mole of any univalent electrolyte solution at 25 degrees centigrade, the value of the Debye length is of the magnitude of 3.1 angstrom. Okay, it is of the magnitude of 3.1 angstrom. So this is all about the Debye Huckel theory, and this was the first part of Debye Huckel theory. In the second part, we will be looking at the Debye Huckel limiting law. Hope the topic is clear. Thank you very much.